Hello, class. So this is just going to be the first in a couple of videos that I'm just going to do about concentration units. So this is just, a couple of different parts of your textbook. I think it's in 18 point, sorry, not 18, 13.4 or so. And it's just talking about different ways we can measure concentration. And so just as a reminder, when we think about concentration, usually what we're thinking about is just a way that we can talk about how much stuff there is in a solution. And so when I say stuff, what I'm referring to is the solute. And what we're going to see is that solute is going to be our chemical species of interest. And we can measure this a couple different ways. Like we can talk about, um, something being qualitatively, having some kind of qualitative concentration of a solution, or we can talk about things being a little bit more specific. So we can have, specific terminology to do so. We can say something's dilute, which, we can all understand to mean that there's relatively little solute in comparison to solvent. We can say something's concentrated, meaning that now we're on the opposite end. We have a relatively large amount of solute in comparison to solvent. And then finally, if we want to be less qualitative, we can be quantitative and we can calculate a concentration. And one of the ways that we've done this most often is using molarity, which is that moles of solute as our stuff divided by liters of solution, measuring, how much there is of that thing in solution. And so there's actually a couple other ways we can describe concentration. And so there's that familiar one of molarity, our moles of solute per liters of solution. There's one called Molality, which you use in the freezing point depression lab, which is all about moles of solute per kilogram of solution of solvent. So we can see that there's two differences here. One, that we have a mass in terms of kilogram, and then between these two, molarity and molality, we've gone from solution to solvent. And so that's going to be something we're going to kind of key in on. We can do something called mole fraction, which measures the moles of solute versus the total number of moles, and that's going to end up being our moles of solute. And if we have multiple solutes, it'll be the moles of all of those solutes plus the moles of solvent. And then we have some measurements that are going to kind of be a little bit different and in some ways less applicable to this hardcore chemistry and more to kind of common sense and things we use in our everyday life. Things like mole percent, which I guess I was a little bit early on this one. Mole percent is just another way to express mole fraction. In this case, you just take the mole fraction, multiply it by 100%, and then we get to those measurements that are a little bit more, related to our real life. And one of those is percent by mass, which just talks about the mass of solute per mass of solution. And so you might say something like, oh, I have a 5% sugar solution, or wash your mouth with a 10% salt solution. And then even more applicable, although we don't really think about it too much, are those measurements of pollutants. So we can have things like parts per million by mass, which you've heard of when we've talked about, different types of pollutants, and that's just the mass of solute per mass of solution. So just like percent by mass, but instead of multiplying by 100%, we multiply by 10 to the sixth because 10 to the sixth is a million. And then we have one more measurement called parts per billion, and that's just the mass of solute per mass of solution times 10 to the ninth. So just, scaling it up a little bit. And so what I'm going to do now is I'm just going to break up these different types of calculating concentration into, little chunks. And so that first chunk is going to be molarity, the one with which we're most familiar. And so molarity is just the amount of solute in moles divided by the volume of solution in liters. And so that means that when we look about calculating it, in the numerator, we're going to put our moles of solute. In the denominator, we're going to put our liters of solution. And so one important thing about molarity is that because this measurement depends upon volume, it's going to end up being it's going to be dynamic with temperature, or we can say that it changes with temperature. Because as the temperature changes, we can see some change to the volume. And so when we have any type of calculation that is going to be, across a range of temperatures, we might not want to use molarity. The units of molarity are just moles per liter, which we have here, and we represent this with that big M if we're talking about something being some specific type of molarity. And the reason that we use it is that it specifies the amount of solute per unit volume of solution. So if I take up, 10 milliliters of a solution, I know that that has a certain number of moles of whatever solute of interest. And so if we're trying to prep a solution that has a specific molarity, we'll get one of our pieces of volumetric glassware. We'll find whatever salt we're trying to dissolve. So if we're trying to make a 1 molar sodium chloride solution, we'll take 58.44 grams of salt, put it in that volumetric flask. We'll add H2O to it to start to dissolve our solution. So we'll add that. We'll keep adding until we get to the blue mark on the neck of the flask, indicating that we are at exactly 1 liter of solution. We mix that up and we end up with a 1 molar sodium chloride solution. And, the important thing here is that we don't actually end up adding a liter of solvent because our solute takes up some space. And so it's all about, focusing on the fact that this is liters of solution. And then if we were to look at the actual calculation for that, we have our amount of our thing, solute in moles, divided by our volume solution in liters, so moles per liter. The other type of concentration that we're going to deal with most often in this class is going to be molality, which, I refer to as the smaller cousin of molarity. And it's pretty similar. In this case, what it's measuring is the amount of solute in moles divided by the mass of solvent in kilograms. So in this case, the numerator is exactly the same. The denominator, however, is a little bit different because we have a mass in the kilograms, and it's going to be the kilograms of solvent rather than the kilograms of solution. And because this measurement is now based off mass of both our moles of solute and our kilograms of solvent, this is going to be something that's constant with temperature. And so if we're trying to observe something that's going to be taking place over a range of temperatures, such as a freezing point depression, this is a preferable unit to use because it's constant. And the units for this are moles per kilogram, and you'll see this if we're referring to a molal solution. We have a little m, and we refer to solutions as having a certain number of molal in terms of concentration. And then why it's used is, because of this temperature independence, it allows the comparison of solutions over a range of temperatures. And the actual calculation is just, as before, moles of solute in the numerator and then kilograms of solvent in the denominator. And when we're faced with a problem, we're given the volume of the solvent rather than the mass, all we need to remember is that we have to use the density to convert volume to mass. And so often you'll see that density is given as grams per milliliter or grams per centimeter cubed. Both of these are equivalent because 1 milliliter is equal to 1 centimeter cubed. But if we need to end up in kilograms of solvent, we're going to want to convert this. And so if I want to do that conversion, what I'll do is I'll just multiply this by, I want 1 kilogram in the numerator. So I'm going to convert from grams to kilograms. And we know that every kilogram has 1,000 grams. And so that cancels out. And in this case, I can also cancel it here. In this case, often we're going to be told that volume, not in terms of milliliters, but in terms of liters. So let's, do another conversion so that we can do a instant conversion from liters of solution to kilograms of solvent. And so I can say that for every 1,000 milliliters, there's 1 liter. And so then I can cancel milliliter and milliliter here. And what I can see is that also, kind of by design almost, the 1,000 for the grams to kilograms and the 1,000 for milliliters to liters cancels out. So what I end up with is that the density of solution in terms of kilograms per liter is going to be exactly the same as the density in terms of grams per mil. Because in essence, we just multiplied each of those by 1,000. So that's something that we're always going to want to keep in mind whenever we do this type of calculation. And so in the next presentation, we're going to go through and do a couple calculations with molarity and molality. Whoops. We go boop.